So in this video, we're going to look at a different kind of wave, a sound wave. We're going to look at how sound waves are made and how they travel. And we're going to be looking at two characteristics of sound, which are the pitch and the volume, and see how to describe those two things using the parts of the wave that we looked at in the previous lesson. It's always initially made by some kind of disturbance, a vibration. Here we have two examples, some speakers, which hopefully you've never seen do this, because that means your music is on way too loud. But what you can see is that the speaker here is moving backwards and forwards. An instrument always has some kind of vibrating part. Here you can see the guitar strings vibrating up and down. All instruments have some kind of vibration. And in fact, anything that makes sound initially begins with some form of vibration. If you put your hands to your throat, you'll be able to feel your vocal cords vibrating. Okay, this is a video of somebody's vocal cords. This is actually what's going on in your throat. Your vocal cords vibrate. This disturbance is what creates your voice. And we'll see how that disturbance changes depending on the note. Tuning fork vibrates to make a really pure sound. And this is a snare drum. I don't know who he is, but he's having a great time. Just look at that vibration on the drum. And guitar strings. Etc. So you get the idea. There's always some initial vibration. So once that initial disturbance happens, what happens to the wave? Well, remember we had our two types of waves. The longitudinal wave. This is the kind of wave that sound, or this is the wave pattern that sound follows. I'll show you that again. The disturbance that's initially made by the instrument is then transferred to the particles which surround it, which is air. Sound must be transferred by a medium. There must be some material that's going to carry that sound. This is very, very different to the idea of an electromagnetic wave, which literally needs nothing to carry it. A sound wave must be transferred by some medium, which vibrates backwards and forwards in a longitudinal wave to carry the vibration to somewhere else. Again, this takes us back to our definition of what a wave is, a transfer of energy. But this way, it's going along the line of vibration. Our transference, our displacement, is along the same line as the wave. You can describe the different parts of that longitudinal wave as compression and rarefaction, as the particles are squashed and then released to stretch out, and then they're squashed, stretch out, so that the particles themselves are vibrating backwards and forwards. But the wave is transferring through. The individual particles of the spring, they move one way and then they come back. They move one way and then they come back. They are oscillating. Now that oscillation has a frequency range, in order for us to hear it, of between 20 to 20 kilohertz, 20,000 hertz. That vibration backwards and forwards within this range means that we can hear it. If it's outside of this range, then what we're dealing with is either sound which is too low a pitch, we can't hear it, or it's very, very fast, too fast for us to pick up, and that would be called ultrasound. This medium which is carrying the wave can be air, but it doesn't have to be. Many animals do communicate in water and in the sea, for example, through sound, dolphins, whales, etc. Now, the medium in that case would be water. Solids also transfer sound, and in fact do it much quicker than air and water, because of course the particles of a solid are closer together, and that transference is much faster. This next video gives you a visualization of what happens to the air around a particle that's making noise. It's a neat video. The technique is explained if you want to watch it in more detail. But here you can see how a speaker disturbs the air around it to create nice waves. This is a book landing. This is a much louder sound, you can see, a gunshot. And you can see how the air is displaced as a disturbance happens. And it carries that longitudinal wave. It's a disturbance, a movement of air particles. How does it become what we now call the complex arrangement of sounds that we know as music, for example, or speech? And that's down to this instrument, which is the ear, an extremely complex organ, which enables us to transfer that information into something very, very complex indeed. What we've got is the earlobe, the ear canal. So this funnels the vibration in. So the air vibrations would continue and they would hit this eardrum. Now this eardrum also vibrates and is picked up by these 3 tiny little bones that oscillate with the eardrum. So we're still talking about a vibration. Now that is then transferred to the cochlea, where there's some liquid which basically picks up that vibration and then eventually transfers it to an electrical signal in the cochlear nerve. Now that's where it becomes something that your brain can understand and interpret. But the vibration is still taking place in most of the organ. Here you can see, hopefully it won't take too long, how that vibration takes place as it goes into the ear. You've got a loudspeaker creating your disturbance, your longitudinal waves. Which then go into your ear and the ear canal. And then hit your eardrum, which vibrates. Now you should understand why we have a limit to our frequency, or the frequency that we can hear, because that eardrum can only vibrate so fast. In fact, it can only vibrate 20,000 times a second, which is still pretty good. Actual eardrum. Okay, you see it's a very, very thin membrane of skin, very easy to damage, all right, which is why you shouldn't stick anything into your ear. So there you go, that's the eardrum. Wave for you briefly. Remember that we can represent a longitudinal wave as a transverse wave. Whenever you see sound waves like this, it's basically a displacement distance graph, right? Or a displacement time graph, but basically showing you the displacement of the particle from its original position, like that, which you can actually show as an XY graph. So don't be surprised if you see sound represented like this sometimes. It's a way to enable you to visualize the disturbances. It doesn't mean that it's a transverse wave. On that note, we're actually going to look at some waves, because now what we're going to do is define pitch and loudness, which are the 2 main ways of describing different sounds. What you can see here is a visual representation of the waves, and you can have your compression and rarefactions this way. Now, one way of thinking about it is your refraction, if I stop it, and compression areas could represent an entire wave. So this would be the equivalent of a crest, for example, and this would be another crest, or it could be a representation of a rarefaction, or a compression and a compression, right? So what you're seeing here is a representation of the wavelength, right? The bigger this distance from one to the other, and in fact, I can use a little ruler here to actually show you an entire wavelength. So if I get my ruler here, I can look at the wavelength from the middle of this dark fringe here, to this one here. And what you've got here is 7, well, I assume it's millimeters, 7 millimeters. That would be our wavelength. So that's one way of looking at the wave in terms of its wavelength. Another way to look at it would be in terms of its amplitude, right? Its intensity. And in this simulation, you can see a much more intense wave as a much darker wave. Now here, what we've got is a wave which has a greater amplitude, right? Because it's much darker. But if I stop it, you should be able to see that the wavelength has not changed, right? So we've got two ways of describing waves: amplitude, wavelength. Once we've got two ways of describing the wave itself, now let's find two ways of describing the sound. So if I now switch the sound on so we can hear it, what we're going to do first is we're going to change the volume of the sound, right? So as you can see, or hear rather, we've made it much, much, much quieter. Let's make it a little bit quieter. There we go. It's represented as a very faint disturbance now because the amplitude has been reduced. And as we make it louder, the disturbance is much greater. Now let's do the same with frequency. I'm going to change the pitch of the sound. And let's see what's happened here. Okay, if I do this, oops, start the wave again. Oh, it's not letting me do it. Okay, let me change it there. Okay, so it should be doing the same as before. What you can see here is the wavelength now is much, much bigger, right? Can you see that? I'll show you the simulation again. Right, what's happened is the pitch is lower and the wavelength has increased. Let's do it the other way around. And as you can see here, this very annoying sound, that what we now have is a very, very, very short wavelength. Right, so amplitude is directly affected by, or directly affects, the loudness. And wavelength influences the pitch. This is high pitch. And this is low pitch. It's a very low sound there. So the lower the pitch, the bigger the wavelength, right? I definitely recommend that you have a bit of a play with the simulation. It will be on the presentation, or a link for you to download. Basically, short wavelength means lots of waves. So basically when you have a high frequency, that means you have a high frequency. Short wavelength, small wavelength, high frequency, and that gives you a high pitched sound. A long wavelength, very low sound, is a very low frequency, right? So now you just need to think about wavelength and frequency. If wavelength is big, frequency is high, and so is the pitch. So have a think about that. Alright, so I hope you've enjoyed this video. If you can watch these last two, they might allow you to internalize what I've been explaining and try the simulation and try today's task.